Well, hey folks, we're going to look at the next section, 4.4. It's the derivatives of logarithmic functions. So we're going to learn some new rules here. And the objectives we're going to focus on in this section will be determine the derivative of a natural log function. And then the next one will be, once we learn a new rule, then we're going to apply the derivative of a natural log function. So we'll see an application example. And then the third and final thing we're going to focus on in this section is determine the derivative of a natural log function using the chain rule. So our old friend, the chain rule. So here we go, folks. Here's your new derivative rule. If you have the natural logarithmic function, f of x equals ln x, as long as x is greater than 0, because remember, can't do the log of a negative number. You can't do the log of 0. So for f of x equals ln x, then the derivative, f prime of x, is 1 over x. So quite simply, if all you see is ln x as the function, the derivative is 1 over x. So let's practice this. Let's look at an example. In this example, we're going to determine the derivatives for the following functions. The first one we're going to do is f of x equals 10 natural log x plus 15. And the second one is g of x equals the natural log square root x plus e to the x. So at this point, you know the drill. Hopefully you've written down the rule here for the derivative of natural log x. And hopefully you've written down this example. Because what I'm going to do now is, well, I'm going to head off to the chalkboard and I'm going to work out this example.
Hey folks, here we're going to do the example that I just left off with. What I thought I would do before I started the example was just to write an abbreviated version of the new derivative rule that we just learned. The new derivative rule is if f of x is natural log x, then the derivative, f prime of x, is 1 over x. And in the example we left off with, there were two parts. Basically, it was get the derivative of the following functions. So in part A, the function is 10 natural log x plus 15. So quite simply, the derivative is, well, remember here you have the constant multiple rule happening. So the derivative is the constant 10 times the derivative of ln x. The derivative of ln x is 1 over x. And then remember, the derivative of a constant is 0. Now, I would multiply these together to get the derivative to be 10 over x. So for the function 10 natural log x plus 15, we have the derivative to be 10 over x. Now, in part B, I'm going to do a little bit of prep work first. In other words, I'm going to do a little bit of algebra. Algebra should help us. Algebra is our friend in a lot of calculus problems. And I'm going to start off with the pesky square root x. Remember, we can rewrite square root x as x to the 1/2 power. So that's going to be my first step, is just to rewrite the function as ln x to the 1/2 power plus e to the x. Now I'm going to use one of those laws of logarithms. We learned them back in algebra. We've already reviewed them. Basically, I'm going to use the law of logarithm that says when I see ln x to the 1/2, there's that property, that law of logarithms, that says I can take that 1/2 and I can move it out front. So I'm going to do that. So far I've just done 2 steps of algebra, but I think now I can quickly and easily get the derivative to be, and again, here's the constant multiple rule, a constant times a function. So the derivative of 1/2 ln x is 1/2 times 1 over x. And then remember the derivative of e to the x, well, we like that. The derivative of e to the x is e to the x. And then I would multiply these two fractions together to get the derivative to be 1 over 2x plus e to the x. And so that's all there is to this example. What I'd like you to do now, let me put a couple problems up here. Pause the video, like we always do, pause the video, And I would like you to try number 9 and number 15 here in the section 4.4 homework. So go ahead, pause the video, go ahead and do number 9 and number 15. Once you've done 9 and 15, restart the video and I'll have the worked out solution for them. Alright, hey, let's see if you got 9 and 15 correct. In 9 and 15, you were just asked to get derivatives for the functions. So when I look at number 9, the function f of x equals natural log x to the 6th, the first thing I think to just make my life easy in the calculus world, to make my process of computing the derivatives easier, is I'm going to use a law of logarithms. I have natural log x to the 6th, so there's a law of logarithms that says I can take that 6 and move it out front. So my first step is just to rewrite the function. That's just using algebra, a law of logarithms. Now to get the derivative, it's the constant multiple rule, so the derivative is just simply 6 times, well, the derivative of ln x is 1 over x, and yeah, I'd multiply those together to get 6 over x. So that's the answer for number 9. That's the derivative for number 9. Hopefully you got that. Let's check out number 15. F of x equals 10 minus 12 ln x. Well, here, nothing to do except start off with calculus, and it's pretty friendly. We remember the derivative of 10 is 0. The derivative of a constant is a constant. This piece down here is going to be the constant multiple rule, the constant times a function. So I just immediately get the derivative to be negative 12 times, well, the derivative of ln x is 1 over x. And then, yeah, just like in number 9, I'd multiply those two together to get negative 12 over x as being the derivative for 15. So I hope you got the derivative for number 9 is 6 over x, and for 15, I hope you got the derivative to be negative 12 over x.
All right, we worked out that example, and we did both parts A and B, and you should have done number 9 and 15. Hopefully you see how to do the derivatives of natural logs. So now it's time to look at an application. So this application, we determined that the percentage of computers that was using the Microsoft Windows 7 operating system can be modeled by the function f of x equals 0.595 plus 12.384 ln x. Note that the restricted domain is 1 less than or equal to x less than or equal to 32. And here x is the number of months since December 2009. And f, well, that's what's giving us the percentage of computers that's using the Microsoft Windows 7 operating system. So here we want to evaluate f prime of 20 and then interpret. You know, very familiar directions that we've seen. Evaluate and interpret, evaluate and interpret. So make sure you write this example down and pause the video if you need to write it down, because my next step is, I'm going to head off to the chalkboard and I'm going to work through this example.
All right, hey folks, we just left off with an example. It's an application. Hopefully you wrote down what the problem was. You wrote down what all the words were. I'm not going to write all the words down, as you've probably learned by now. I'll read them real quick. The example was the percentage of computers using Microsoft Windows 7 can be modeled by the function f of x equals 0.595 plus 12.384 ln x, and the domain for it is x is between 1 and 32. X represents the number of months since December 2009, and the function itself represents the percentage of computers that would be using Microsoft Windows 7. So in the example, you're asked to evaluate the f prime of 20 and interpret. Well, in order to do f prime of 20, we first need to get f prime of x. So you look at your function and you need to compute the derivative of the function. And let's see, that's a constant, so the derivative of a constant is 0. And then way down here you have the constant multiple rule, constant times a function. So the derivative would just be 12.384 times the derivative of ln x, which is 1 over x. And yes, I could clean this up to 12.384 over x. Well, now that I have the derivative, it's a relatively easy process for me to evaluate the derivative at 20. I just toss 20 in for the x, so f prime of 20 is 12.384 divided by 20. And when I crank this through my calculator, let's see, I get something pretty close to 0.6192. So we've evaluated the f prime of 20. Now let's think about the interpretation. See, 20 is in place of x. X is the number of months since December 2009. So I guess this 20 would mean 20 months since December 2009. Let me start writing down this interpretation right here. So 20 months since December 2009, which 20 months since December 2009, I guess I could have just counted 20 months since December 2009, and that would have brought me to August 2011. So really I'm in August 2011. The percentage of computers using, let's see, what are they using? Windows 7, Microsoft Windows 7. So the percentage of computers using Windows 7 was, okay, now remember, this is a rate. The derivative gives us a rate. It's a positive number. Positive number, and it's a rate. That means it was increasing. And it was increasing at a rate of, all right, so now this is a percent, so it's increasing at a rate of 0.6192. That's this number, increasing at a rate of 0.6192%, and then it was per month, because our independent variable is in terms of month. One more time, we've seen this a lot already, but when you're interpreting a derivative, it is a rate, so you need those units, those rate units, per something. Here it's per month. So that was the example we left off with, and what I'd like you to do is I'd like you to pause the video and try an application in the book. So let me just write that number right here, number 53. So I'd like you to pause the video. I'd like you to go into the exercises here in section 4.4. I'd like you to try number 53, and then after you do number 53, restart the video, and I'll be here at the chalkboard and work out the solution. All right, folks, here in number 53, it says, in order to regain revenue that has been lost to third-party couriers, the United States Postal Service adopted a flat parcel shipping rate during the mid-2000s. The annual USPS, United States Postal Service, revenue from 1991 to 2010 can be modeled by this function, f of x equals 38.16 plus 12.22 ln x, on the domain 1 less than or equal to x less than or equal to 20. And here for this function, x represents the number of years since 1990, and f of x represents the USPS revenue in billions of dollars. You were asked to do two things here. In part A, you were asked to determine f prime of x, and then in part B, you were asked, according to the model, how fast was the USPS revenue growing in 2009 as compared to 1999. So here, let's get started. First, let's do part A. Part A was just simply, get the derivative. So hopefully this is old hat. It's becoming old hat by now. Here's your function, the derivative of the constant 0. This is the constant multiple rule, a constant times a function. So the derivative is 12.22 times the derivative of ln x, which is 1 over x. And yes, I'll write that as 12.22 over x. So for part A, the derivative is 12.22 over x. So now in part B, when you're asked to compare how fast, let me read it again. According to the model, how fast was the USPS revenue growing in 2009 as compared to 1999? So you're really being asked to evaluate the derivative at two different values of x. So let's first look at 1999. Well, 1999, if x is the number of years since 1999, 1999 would have a value of x to be 9. So what we have to do is we have to evaluate the derivative at 9. That will tell us how fast the revenue was changing in 1999. So let's go ahead and toss 9 into the derivative. And we get f prime of 9 is 12.22 over 9, which according to my calculator, when I take 12.22 and I divide it by 9, I get something pretty close to 1.358. Okay, now we've evaluated a derivative. That means there have to be units attached to it. So what are these units? Well, it's 1.358 billions of dollars. It's billions of dollars. So I'll just put the dollar sign here, and I'll just put billions here. Billions of dollars per year. So in 1999, the USPS revenue was increasing at a rate of $1.358 billion per year. Let's see what's happening in 2009. So let me go ahead and just put a little break here. 2009, well, let's see. If x is the number of years since 1999, since 1990, for 2009, x would have a value of 19. 2009 is 19 years since 1990. So now we have to take that 19, and we toss it into the derivative. We need to evaluate the derivative at 19 to tell us how fast the revenue for the USPS was changing in 2009. So we go ahead and evaluate the derivative at 19. So we take 12.22 divided by 19. And when I do that, crank that through my calculator, I get something pretty close to 0.643. And again, we've evaluated a derivative, so it would have units. So I would say that's billions of dollars. Oop, barely fit it on the board. Per year. So when I compare the two rates, I can see in 1999, the USPS revenue was increasing at a rate of about $1.358 billion per year, whereas in 2009, the USPS revenue was increasing at a rate of about $0.643 billion per year. So it looks like in 1999 it was increasing at a faster rate than it was in 2009, because this number is larger than that number. So hopefully you got number 53, and we're going to head back now to PowerPoint slide, where we're going to learn one more new thing about natural log functions. One more new thing, specifically how to use the chain rule.
All right, hey, welcome back. We worked through that example, and hopefully you understood number 53 as well. So the final thing we're going to look at in this section is going to be the chain rule. So here it is. Here's the chain rule. If g is a differentiable function of x, and the range of g is 0 to infinity, that's just a little disclaimer for our making sure we don't do the natural log of 0 or a negative number. Then the derivative of the composition of functions, and notice how it's written, h of x equals the natural log of g of x. So just think, you're going to have the natural log of a function of x. Say the natural log of 2x plus 3, or the natural log of x squared. It's not just going to be natural log x anymore. So if you have the function h of x equals ln of g of x, then the derivative is going to be 1 over g of x times g prime of x. In other words, it's going to be 1 over whatever this function of x is times the derivative of this function of x. That's it. We're going to do an example. So determine the derivatives for the following functions, and I have 2 of them here. In part A, it's going to be g of x equals the natural log of the cube root of 2x minus 5. Bet I do a lot of algebra first there. And then in part B, the function is h of x equals x squared times the natural log 2x. That's kind of cool. It looks like we're going to revisit the product rule on that one. So, hey, go ahead, write this example down because my next stop is off to the chalkboard to work out the example. So write it down, and here we go. We're heading off to the chalkboard.
Hey folks, we just learned about the chain rule with the natural log functions, and I wrote an abbreviated version of the rule that you just saw on the PowerPoint slide up here in the upper right-hand corner of my chalkboard. And basically it says if you have a function h of x that's equal to the natural log of some function of x, then the derivative is 1 over g of x, it's 1 over whatever that function is, times g prime of x, times the derivative of that function. So in short, it's 1 over this junk times the derivative of that junk. So let's look at the example we left off with. Hopefully you wrote it down. I asked you to get derivatives for the following functions, and there were 2 parts. In part A, the function was g of x equals the natural log of the cube root of 2x minus 5. Okay, folks, I'm going to do some algebra first here to make the calculus world much, much easier. If I don't start off with this algebra, my calculus will be very, very cumbersome, difficult, ugly. I don't even want to think about it. So here's how I'm going to start off. Cube root. We know we can rewrite cube root as an exponent of 1/3. So my first step is just algebra, rewriting the cube root of 2x minus 5 as 2x minus 5 to the 1/3 power. I'm still going to use algebra. I'm going to use one of those laws of logarithms. That I have the natural log of 2x minus 5 to the 1/3, there's a law of logarithm that tells me I can take that 1/3 and just move it out front. That's algebra. So let me do that. G of x is equal to 1/3 natural log 2x minus 5. So I've done 2 steps of algebra. Now the calculus should be much friendlier for me to do. So to do the calculus here, to get the derivative, g prime of x, I first note that I have again the constant multiple rule. I have a constant times a function. So to get the derivative, using the constant multiple rule, I have a 1/3 times. Now to get the derivative of ln 2x minus 5, what the rule is telling me is I just simply take 1 over this function. It's this piece right here. So 1 over the 2x minus 5, and then times, and here's where your chain rule comes in, times the derivative of this function. Well, what's the derivative of 2x minus 5? It's just 2. So again, ln 2x minus 5. That's ln of a function of x. To get its derivative, we do 1 over that function of x, 1 over the function of x, times the derivative of that function of x, times the derivative of that function of x. And, you know, I would probably instinctively here multiply those three fractions together. 1 times 1 times 2, so it gives me a 2 over 3 times 2x minus 5. So I would just naturally do that, and I'd say, hey, there it is. That's the derivative. So for part B, I'm going to have to erase the board to get part B up here. So bear with me. Part B, the function was h of x equals x squared times the natural log of 2x. Well, hey, what's kind of cool here is we get to use the product rule. See, all these old rules, they're still playing the game. So remember the product rule. I have a function, x squared, times another function, ln 2x. So let's go through, and I'm going to babble the English to the product rule. Remember, when you use the product rule states derivative of the first function, so that's 2x, times the second function, plus the first function, which is x squared, times, now the derivative of the second function. So when I do the derivative of ln 2x, the derivative of ln 2x is 1 over 2x times, remember your chain rule, times the derivative of that 2x. Well, what's the derivative of 2x? Just 2. And you know, if you want, you could clean this up just a little. This is 2x ln 2x. But if you multiply all this junk together and you cancel what will cancel, the 2 will cancel with this 2. This x squared, well, one of those x's, an x squared, would cancel with that x down there. So x squared times 1 over 2x times 2 simplifies to x. Okay, 2's cancel out, and that cancels with that. Boop, that's it. So that's it for part B. That's the derivative. I'm going to leave it in that form. And need you to practice. I need you to practice the chain rule. So what I'd like you to do is I'd like you to pause the video, head off into the homework to number 23. So head off, go do number 23. After you've done 23, restart the video, and I'll have a worked out solution. Hey folks, here at 23, you were asked to get the derivative for the function f of x equals the natural log of square root 2x plus 5. You know, I'm going to start by using algebra. I'm going to rewrite that square root as an exponent of 1/2. So my first step is just algebra. In fact, my second step will be algebra. It's using that law of logarithms, moving that 1/2 out front. So my first two steps are just simply algebra. Now I'm ready to do some calculus. So I get the derivative to be 1/2 times, okay, so the derivative of ln 2x plus 5, that derivative is 1 over 2x plus 5 times, now the derivative of 2x plus 5, which is 2. And if I clean this up, if I multiply these fractions together, a neat thing happens. We know 1/2 times 2 is 1, so I'm just left with 1 over 2x plus 5. And that's it for number 23. So that's basically it. That's the last thing we're going to do here in section 4.4. So at this time, you should be ready to, hopefully you've read through the book also. Besides watching this video, you've looked at the objectives that I had highlighted to look at. You've done everything. You're ready to go attack the homework problems. So go do the homework problems, and hopefully they treat you quite nicely. Thanks for watching.